A submarine can dive deeper than a skyscraper is tall, stay submerged for 6 months, and carry enough firepower to end civilizations. Here's how it actually works, explained in 10 minutes. A submarine is a spacecraft for the abyss. It has to generate its own air, its own water, and its own power, all while surviving crushing pressures that would fold a skyscraper like a tin can. It's the only machine that deliberately hides from the world to do its job. Every submarine is built to do something insane, sink itself on purpose, because the ocean is trying to kill it. Every 10 meters down, pressure climbs by 1 full atmosphere, deep enough that pressure would crush a human chest instantly. Past 200 meters, there's no sunlight left, total darkness all the way down, no air, no radio signal, no rescue. So 3 problems have to be solved before anyone even builds a hull: survive crushing pressure, breathe without the surface, and navigate blind. Get one wrong and the ocean doesn't warn you, it just wins. Some attack submarines cruise deeper than the Eiffel Tower stands tall, in total blackness for months. But floating isn't the hard part. Sinking on command and stopping exactly where you want, that's the real trick. A submarine floats or dives using ballast tanks, huge empty compartments built into the outer hull. On the surface, they're full of air, just like a ship's hull, keeping the boat buoyant. To dive, the crew opens vents at the top. Air rushes out, seawater floods in through ports at the bottom. Weight increases until the submarine matches the water around it, neither floating nor sinking, just hanging in the deep. Once submerged, smaller trim tanks fine-tune the balance, shifting tiny amounts of water forward or backward so the boat holds depth without drifting up or down. To surface, high-pressure air stored in steel flasks blasts back into the ballast tanks, forcing seawater out the same ports it came in. But sometimes there's no time for that. In an emergency, every ballast tank floods with air at once. Thousands of liters of compressed air detonate into the tanks simultaneously, and the submarine lunges upward like a breaching whale, rocketing to the surface in under a minute. It's violent, it's loud, and it's the very last option when something below has already gone wrong. Even if the ballast system works perfectly, the crew still faces a much bigger problem. What stops 300 tons of ocean from crushing everyone inside at once? The answer is the pressure hull, a thick cylinder of steel or titanium that keeps the crew compartment at surface pressure no matter how deep the boat goes. Most modern submarines use a single hull design, one strong pressure cylinder wrapped in a thin outer casing for smoother handling underwater. Older Soviet designs used double hulls instead, an extra layer of steel for survivability at the cost of extra weight and a slower, clumsier boat. That's the trade-off: protection against speed. Every hull also carries 2 critical numbers. Test depth is the maximum it can dive to safely again and again. Crush depth is far deeper, the point where the hull physically fails. For modern attack submarines, that's estimated near 800 meters, almost twice the height of the Empire State Building, straight down. Past that line, the hull doesn't leak, it implodes, the entire vessel collapsing in a fraction of a second. Faster than a nervous system can register pain. Steel keeps the ocean out, engineering keeps the crew alive. The hull survives, but now 150 men need to breathe for 90 days straight, with no windows and no fresh air. So the submarine manufactures its own atmosphere from nothing. An oxygen generator splits seawater into hydrogen and oxygen using electricity. Hydrogen vents overboard oxygen pipes straight into the boat. Meanwhile, carbon dioxide scrubbers pull the gas the crew keeps exhaling out of the air, using a chemical absorbent that grabs onto CO2 molecules before they can build up to dangerous levels inside the boat. If both systems ever fail at once, there's a last resort: oxygen candles, chemical canisters that burn to release pure oxygen, kept sealed for true emergencies only, and trusted by every engineer aboard with 150 lives. Fresh water comes from evaporators or reverse osmosis units, desalinating seawater for drinking, cooking, and cooling the reactor itself. Put it together, and a nuclear submarine can manufacture almost everything the human body needs to survive indefinitely: air, water, even power. The only thing it can't make from seawater is food, and that, more than any machine or reactor, is what quietly limits how long a crew can stay down. Air solved, water solved. But down here, there are no windows and no light past 200 meters. So how does a submarine see anything at all? It doesn't. It listens instead, using sound the way human eyes use light. Sound travels roughly 4 times faster underwater than in air, and far further than light could ever reach. So submarines rely entirely on sonar instead of cameras or radar. Passive sonar simply listens. Sensitive hydrophones pick up another vessel's sound signature. Its engine noise, its propeller cavitation, even the specific hum of its machinery, without ever revealing the submarine's own position. Operators track this on a waterfall display, where sound frequencies scroll downward over time. And trained ears learn to recognize individual ships purely by their acoustic fingerprint alone. Active sonar works differently. It fires a sound pulse and listens for the echo, giving exact range and bearing instantly. But that pulse also announces the submarine's exact location to anyone listening nearby. That's the trade-off engineers accept. Active sonar sees clearly, but it's often called a death sentence. Because the moment you ping, every enemy within range already knows exactly where you are hiding, instantly. For most of submarine history, endurance was the real limit. Diesel-electric boats had to surface constantly to recharge batteries and refill air, exposing themselves to detection, sonar, and attack every single time they came up for air. Then came the nuclear reactor, and everything changed overnight, permanently. Controlled nuclear fission generates heat. That heat produces steam, and the steam drives turbines for propulsion and electricity. No air, no fuel tank, no surfacing required ever. The result is staggering. A nuclear submarine can operate for over 30 years without ever refueling, longer than most naval careers even last from first enlistment to retirement. The only real limit left is food and crew endurance, not power, not fuel, and not air. This single piece of engineering turned submarines from short-range ambush weapons into vessels that could circle the entire globe underwater without surfacing once. Arguably, it's the single biggest leap in naval history since the steam engine itself replaced the sail on every ocean on Earth. Submariners call their own branch the Silent Service because for decades their missions weren't even officially acknowledged to exist. Months without sunlight, no contact with family, constant awareness that one mistake, one hull breach, means there's no rescue coming at all. That isolation builds something rare: total trust between crew members few other military roles ever require. The submarine isn't fighting the enemy. First, it fights physics. That's how a submarine works. From the ballast tanks that let it vanish beneath the waves, to the nuclear reactor that lets it stay there for months. The deeper we go, the more the picture shifts. Stick around for what's next. Hit subscribe and stay locked in. Hardware of peace, weapons explained, power revealed, no politics,